This is the first video on implicit differentiation, and we're going to look at what implicit really means in this context. We've got two expressions here. Explicitly, we tend to express y as a function of x, and you should be very familiar with that if you're watching this video. Implicit is different, although by now you've probably seen things expressed implicitly. And we can convert between the two often, but sometimes it might not be convenient if things are given in an implicit manner to convert to explicit, and sometimes it's not really possible. So in an implicit relationship we have f of x and y of both, and that would be equal to some constant in an equation. A variation on that might be g of x and y equals 0. But 0 is constant. So if we consider x times y equals 1, we can look at that in two ways. We can basically make it is implicit like that. Okay, we have an f of x and y equals some constant, and we could easily convert this particular one. If we say y equals 1 over x, we just rearrange, and if convenient, we would write it as x to the negative 1. So y equals 1 on x, or y equals x to the negative 1. We're going to call that statement 1. So if we take the derivative of that, that's easy to do, and we've got negative x to the negative 2, or if we like, putting it back the way it was as a fraction, negative 1 over x squared. I'm going to call that statement 2. Okay, the other way of looking at this given equation and finding dy dx, we can use the product rule, and we can differentiate both sides. Okay, so what I mean by that is that we can, if we want to find dy dx, we can take the derivative with respect to x of the left side, which initially would look like that, and the derivative with respect to x of the right side, which would look like that. Derivative of a constant is 0. So what we need to do now is apply the product rule, and you can see that the two parts of the product are x and y. Now if we use the product rule pattern, we would have the first part of the product, x times the derivative of the second. So the derivative of the second is the derivative of y with respect to x. You could even make it a bit more explicit like that. And following the product rule pattern and continuing on, we have x times dy dx, no change there. Dx dx is 1, and so we just got 1y, that equals 0. And then we can rearrange. So we've got x times dy dx equals negative y, and so dy dx I should say, dy dx equals negative y over x, and that doesn't look like it, but it is the same as what the other method yielded, because we can substitute the value of y in there, which is 1 on x, alright, and it's the same as statement 2 from above that I identified. You can scroll that back if you need to. So the process is called implicit differentiation, and it's used when it's inconvenient or sometimes it's impossible to write y in terms of x. And a couple of examples penned there. You've got an ellipse there, and some hybrid function of an exponential base e and a sine. And basically, yep, those are very difficult / impossible to write in terms of y equals f of x. It either takes a huge amount of time and energy to make it not feasible to do, or it's just not possible to express something as a function of x in terms of y, of y in terms of x I should say. Now it uses an axiom of mathematics that should make sense, and it uses the axiom that if two expressions are equal, then the value of each expression must change in an identical way as one of the variables changes. So if we have a with the a as an expression or a function of x and y, and we have b, which is also set equal to that, and it's also a function of x and y. These things here hold, so the derivative of that a with regards to x will equal the derivative of b with regards to x, and dA dy will equal dB dy. Okay, if a and b are functions of x and y. So it is based on an axiom. So if we consider x equals y squared and we have to find dy dx, we can use implicit differentiation. So we take the derivative of both sides with regard to x, so you can see that happening there. Okay, so far so good. And 1, and then we need to consider the derivative of this side here. Now we're going to use a chain rule here, okay, and make a substitution. So we let some other unused letter, variable, symbol, let u equal y squared, so du dx is du dy dx. It's following the chain rule. And if u equals y squared, du dy is 2y, and dy dx is dy dx. So basically 1 equals, let's make that x look a bit better, 1 equals that result along the side there, 2y dy dx. And that x2 is not great. There we go. Okay, and isolating dy dx, because that's what we're finding, we have 1 over 2y, where y cannot equal 0. So that's a good one to use with implicit because it's problematic. So if y squared equals x, then y equals plus or minus the square root of x, okay? And then we have an issue with the vertical line test. Okay, so we'll have this sort of scenario. So both of those together do not constitute a function. In this example, we've got our good old friend bargain basement circle there, and the center is at the origin, radius of 1. And what if we have to find the derivative? Okay, so it's not a function, so putting it as f of x, y equals f of x, y is a function of x, is not feasible for us to do. So we'd use implicit differentiation on this. So finding dy dx, we basically use the property of the sum of the derivatives equals the derivative of the sum, and so basically this, and do it to both sides according to the axiom. We split them up, and sum them together. Okay, that's 0, easy to compute there. That's 2x, and that's where we use that same process from before. I'll speed that up this time, refer to the previous example. Here, 2y dy dx. Rearranging to get dy dx. Negative 2x over 2y. Negative x and y is our value for dy dx. Sometimes we can use two methods. We can pick between our methods. We're going to show both for this one here. Xy minus y minus x squared equals 0. We've got to find dy dx. And sometimes, like in this one, there's not much difference between them in terms of which one's the easier method. So method 1, putting things in terms of y equals f of x, we need to rearrange. So I'll do that first here. So this is method 1 starting here. So I've started rearranging that, and we've got y equals x squared over x minus 1. And now it's a pretty easy job to take the derivative of that. You've got a choice. You can use polynomial division, and you can get x plus 1 plus 1 over x minus 1 if you want, and then you can find the derivative of that. Very easy to do, and that might involve a little bit of a simple quotient rule or very simple chain rule, or you can just plug in the quotient rule from there, and you get, I'm leaving the working out because this is assumed knowledge well and truly, and you'd get x squared minus 2x over x minus 1 all squared. So just remember that result. I did leave a lot of the working out. The actual process itself takes longer than that. Using implicit, we get this, and then we have to use a product rule here like we saw before, I think, and I seem to remember doing a product rule early in this video. We've basically got to apply the product rule process. I might be applying the pattern in a different order to what you might have had in mind. So, but it comes out, it's very user-friendly, the product rule. Okay, so we have d dx of x times just y, plus we have x times dy dx, and we have dy dx. We can just write that in as just plain dy dx. That's this one here. It's not going to change now, and that one is 2x, and that is 0. Now we just have one y there, and x, we leave it as x dy dx in the second term there, dy dx, another term of dy dx there, and 2x there. We can treat dy dx algebraically, and we've got one lot of dy dx there, so basically we've got x minus 1 outside of dy dx, simplifying, plus y minus 2x. We have rearrangement happening here, and we have x minus 1 dy dx equals 2x take y, and dy dx is 2x take y over x minus 1, and we have a result there. You don't need to go any further than that, so there's our result. But just if you ever wanted to verify it, remember last time doing it the other way we got that. So we can show, since we know that y equals x squared over x minus 1, we can sub that in, and we can as an interesting exercise show that it does equal this. So if we have 2x take y, and it's over x minus 1 all squared, so to get something like that, we start by splitting it up, and we've got top and bottom squared, so that'll be the numerator denominator squared there, and we sub in x squared over x minus 1, that's instead of y, over x minus 1. I haven't squared the top and bottom there, have I? Okay, then that would be 4x squared over x minus 1 all squared, and this would be x squared over x minus 1 all squared. Oh no, I've just looked at what I did, and that's crazy. I've just done something really incorrect here. I've squared top and bottom, but I'm trying to get an equivalent fraction here. I'm not squaring it. I just want an equivalent fraction such that the denominator is x minus 1 all squared. I'm going to leave that x minus 1 all squared there, but I can't square that. I have to multiply top and bottom by the same thing to retain the equivalent fraction. That's madness. So I will correct that right now before your eyes, and we will fix that. Okay, better. Alright, so here we go. We got on the left term there, we've got 2x, just expanding, 2x squared minus 2x over x minus 1 all squared, and as before we can send that x minus 1 down to the bottom. It's multiplied with the other x minus 1, so it's x minus 1 all squared, and now we've got a simple subtraction to do, and the result is the same as the one above in green, and that's verified. You don't need to do that usually, but it's an interesting activity, especially interesting when you make a funny mistake in the middle, and satisfying when you spot your own mistake and fix it up. So x squared minus 2x over x minus 1 all squared